All right, in this video, we're going to continue the 2.3 notes. So this is part 2. Part 1 was on IR spectroscopy. That is a different video. We're going to cover the isomer flowchart, which is on Blackboard, and configurations of alkenes in this video. So let's go ahead and get started with the flowchart. Now, if you go to our Blackboard site, open up Content, Handouts, you'll be able to see this isomer flowchart handout, and that's what I have included in my notes. So you can reference this online. You're not really required to print it. It's just an available resource for you. As you're looking at this, let's talk through what's on this flowchart. So far, we've talked about 2 different types of isomers, and we're going to talk about a third today. But let's start. Let's say you have 2 compounds that have the same molecular formula. If they are completely superimposable, meaning you can either twist, or not twist, but you can take one and flip it upside down and you'd get another, or stand it up, then you'd get another. Those are identical structures. So look at these 2 first ones here where my mouse is pointing. If you take the structure, these look different, right? But if you take the structure on the right, flip it 180 degrees with the plane of the paper. So the 2 chlorines are on the right. The CH3 group will be on the bottom left and the hydrogen will be at the top. And then flip that from bottom to top. Then you have the CH3 group on the top, hydrogen on the bottom, Cl on the right for both. So these 2 are identical. Or this one might look more familiar, the 2-cyclohexane. This is a 1,3 dimethyl cyclohexane, 1 points up, 1 points down. Over here, we have 1,3 dimethyl cyclohexane, 1 points up, 1 points down. If you took one of them, flipped them upside down, you'd get the other. We're not doing any bond twisting to convert between these 2. They're identical structures. We have 1 methyl equatorial, 1 methyl axial on each one. We could just flip it upside down and you'd get the same as the other. Okay, so those are identical structures. Any pair of compounds beyond this point, so that are not completely superimposable, they are isomers. So if 2 compounds with, don't forget, they have the same molecular formula. If they have different atom connectivity, these are the constitutional isomers. So this first example is perfect. We have a cyclopentane ring, a bromine substituent, and a methyl substituent. Here we have a cyclopentane ring, a bromine substituent, a methyl substituent. But on the second one, the bromine is bonded to 1 carbon and the methyl is bonded to a different one. In the first structure, they're bonded to the same carbon. These are not the same molecule. They have the same formula, but you cannot convert one into the other by bond twisting. You cannot establish a mirror image of one to get the other. That's a different isomeric relationship. So these are 2 different structures. They'll have different names. Those are constitutional isomers. If we have molecules that have the same molecular formula, are not the same exact structure, do not differ by atom connectivity, but are still not superimposable, these are called stereoisomers. So stereo, think about areas of space for stereo, like stereo surround sound, right? Like the sound is taking up the space around you. Stereoisomers have atoms in different arrangements in space. They'll have the same connectivity, but are not the exact same molecule. So here are 2 that we've talked about so far under conformational isomers. We've talked about conformationals. So these are both 1,3-dimethyl, but you cannot convert one into the other by just simply taking the molecule and flipping it upside down. You have to rotate those bonds. These are chair flips of a molecule that is a conformational isomer. Here's another one that we've seen are these Newman projections. So let's see, this first Newman projection, well, they switch the front and the back carbon, but they've also have the CH3 groups gauche to each other here and opposite to each other here. So this is an anti and this is a gauche. Those are conformational isomers. They have different energies, but the connectivity of the atoms is the same, and you can convert one to the other by bond twisting. All right, so we're going to move on to configurational isomers here. So a different type of isomers. These are two objects that are not superimposable, and they may or may not be mirror images of each other. We're going to start with, no, not mirror images. We'll start with diastereomers. There are no alkene examples, so carbon-to-carbon double bond examples in this chart, but that's where we're starting. We're going to talk about alkenes that are diastereomers. So same molecular formula, do not differ by atom connectivity, but they differ by the arrangement of atoms in space. All right, here we go. Configurational isomers, and we'll talk about diastereomers. All right, talking about alkenes, and I'm going to put a little note here that only some alkenes exist as configurational isomers. We'll come back to that. We'll talk about alkenes that are configurational isomers first. So here's an example for you. 2-butene. Butene, we have 4 carbons. 2-butene means that the double bond is at carbon 2. So here is 2-butene. If we convert this to a Lewis structure, we can have carbon-to-carbon double bond in the middle. The carbon on the right is bonded to a CH3 group and a hydrogen. And the carbon on the left is bonded to a CH3 group and a hydrogen. This is one way to draw 2-butene. Another way to draw 2-butene, if we focus on these methyl groups, relative to where the double bond is, one is on top of where the double bond is, above the double bond, and one's below. Now we can also draw 2-butene where both methyl groups, both CH3 groups, are above the double bond, or what we'll say on the same side of the double bond. So now they're on the same side. Both of these molecules are 2-butene. But they have a different arrangement of atoms in space. Now we've seen these types of molecules like chair flips. They're both the same connectivity of atoms, but different arrangement of atoms in space. With chair flips, you can convert between one chair flip to the other for the same molecule by rotating around the carbon-to-carbon single bonds, because single bonds can rotate. But what's important here is that pi bonds, so a double or triple bond, those cannot rotate. So we cannot rotate around this carbon to carbon bond to achieve that first structure. It's impossible. It cannot happen. So these are now two different molecules. So both are 2-butene, but have a different arrangement of atoms in space. To convert one into the other, you'd have to break a bond. You cannot twist a pi bond. It's a star here. Wow, that's a terrible star. Here we go. Pi bonds do not rotate. Okay, so this means that these two are two different molecules and they need to be named differently. So we're going to add to our nomenclature notes for instances where there are configurational isomers. So because of all of this, they are different molecules and need to be named differently. Now, I'll tell you what the names are of these two molecules, and then we'll go through the steps of how to determine what the name will be. So they're both 2-butene. We're not changing that. All right, that follows our nomenclature rules. You can also write but-2-ene. That was the other way. That's correct. If you look at the book, it states that both are correct. You can change where you put that number. The one on the left is called E-butene, and the one on the left is Z-2-butene. So E2-butene and Z2-butene. We use E and Z for double bonds, kind of like we use cis and trans for rings. So E is like saying trans, where those two high priority groups are on different sides of the double bond. And Z is like saying cis, where the two higher priority groups are on the same side of the double bond. All right, let's go through the steps of how to name these types of molecules. Step 1 is prioritizing the two groups bonded at each end. By each end, I mean each carbon that's part of the double bond. So I'll write out that detail. So prioritize the two groups bonded to each carbon involved in the double bond. We'll do one carbon at a time. When doing this, the group with the highest atomic number at the first point of difference gets first priority. Let's add a picture to this here. So if you're looking at a carbon-to-carbon double bond, each one of these carbons, if it's part of a double bond, it's going to have two other groups there, bonded to two other things. So we look at the two groups bonded to each carbon involved in the double bond, one carbon at a time. So you look at the carbon on the left and assess what is directly bonded to it and prioritize one of those two groups. And then you do the same thing for the carbon on the right, check out what's bonded to it, and prioritize one of those two groups. So let's go through that process for the 2-butene. We'll do E2-butene first. So in this case, the way I drew it above, we had this bonding pattern. Okay, so let's look at the left side first. So we're going to look over here, looking at this carbon, the two groups directly bonded to it. That is a hydrogen and a carbon. Comparing hydrogen and carbon, those two are two different atoms. So we've reached the first point of difference. And carbon has a higher atomic number. So this is the first priority group for the carbon on the left, for the carbon involved in the double bond on the left. For the carbon involved in the double bond on the right, then we do the same thing. We look at the two groups bonded to it, find the first point of difference, and in this case, it's the atom directly bonded to that carbon. So we're comparing carbon from the methyl and hydrogen. Carbon has a higher atomic number than hydrogen, so that gets first priority. All right, so we've looked at each carbon that's part of the double bond and the two groups bonded to it. And in this molecule, we have the first priority group on the left and the first priority group on the right on different sides of that carbon-to-carbon bond. By different sides, we consider splitting between the two carbons involved in that double bond. So where I just drew that gray hashed line. One is on one side of that line, one's on the other. They're on different sides. Okay, so step 1, step 2, if the two priority groups, so if they're on, we'll write directions for if they're on the same side. We'll write directions if they're on different sides. So if they are on different sides, like we have here, of that carbon-to-carbon double bond, This gets an E. That's supposed to be an arrow. I'll make that more obvious. As a prefix. And this comes from, I think this is a German word, Entgegen. If you're German and you're laughing at me, I am sorry. Which means contrary. So if we go back to our original structures, that first one that we drew with the two priority groups on opposite sides of the double bond was E2-butene. Then if the two priority groups are on the same side of the double bond, the prefix Z is used. And this comes from zusammen, meaning together. And when I was learning organic chemistry, my instructor taught us that if the groups are on the same side, we use Z. So Z for same side. And that seemed to be helpful, at least for me. All right, so that first molecule that we just did that priority for, this was E2-butene. Let's do the same thing for the other diastereomer or other configurational isomer of 2-butene. So that is carbon to carbon bond, CH3 and H, same as the original. And then for the carbon on the left, the CH3 and hydrogen have switched spots. So looking at the carbon on the left, the priority group is here. Carbon on the right, priority group is here. Imagining that splitting between the double bond. Priority group on the left and priority group on the right are on the same side of the double bond. So this is Z2-butene. Now sometimes the Z and the E are in parentheses. I don't mind either way, but just keep that in mind. You might see that. All right, let's talk a little bit more about the relationship of these two and add some lingo. So these two molecules are relatives of each other. They have the same connectivity. We've talked about this. So each of these has a CH3 group bonded to a carbon that's double bonded to another carbon that's bonded to a CH3 group. That's the same, that's what we mean by same connectivity. So they have the same connectivity, but they have a different arrangement of atoms in space. They cannot be interconverted by bond twisting. And the last criteria that probably doesn't seem relevant right now, but it will next week, is that these are not mirror images of each other. You could not reflect one and achieve the other, is what we're saying here. So all of this means that these configurational isomers that meet these conditions are diastereomers. All right, let's do some practice before I end this video here. So when we talk about stereoisomers, we can refer to their properties as stereochemistry. So I'll draw a few structures. You'll determine if they have E or Z stereochemistry. Then, or let's say if so, draw the other configuration. Another way to say this is the other diastereomer. Those indicate the same things. All right, here's our first structure. All right, here are 3 molecules. You'll determine if they have E or Z stereochemistry, and if so, draw the other configuration or the other diastereomer. So you might pause, try working through using these 2 steps here. Try a little bit more than 2 steps, but I wrapped them up into 2, and try to determine E or Z stereochemistry for those examples. So again, you can pause here. I'll go ahead and continue working through these though. So the first thing we do is look at each of the 2 carbons that are in the double bond. So I'm going to call one pink and one blue. So the one on the left, we look at the 2 groups bonded to it, and the one on the right, we look at the 2 groups bonded to that one. So the pink carbon is bonded to a chlorine and an oxygen. We've already reached 2 different atoms, so we compare the atomic numbers of oxygen and chlorine. You look at the periodic table, chlorine has a higher atomic number, so chlorine for the pink carbon is the first priority group. All right, now we go to the carbon on the right. Carbon on the right is bonded to a bromine and a carbon. Remember, there's a carbon right here. I'm going to erase that, but remember that's a carbon. Bromine and carbon, two different atoms. So I'm starring where we reach the first point of difference. And then if you compare atomic numbers of carbon and bromine, bromine has a higher atomic number. So that is the first priority group. Now, looking at where these two groups are, they're on opposite sides of that double bond. Remember, that double bond cannot rotate. So this has E configuration. Just to draw that dashed line again, this is what we mean by different sides. We have chlorine, the first priority group on that side, and then the first priority group on the other. All right, so this is E. To draw the other diastereomer, you can switch the locations of the groups on the blue carbon or the location of the group on the pink carbon, but you can't do both because then you'd end up with E again. So I will change where the groups on the blue carbon are. So I would take the same Cl and methoxy group. Then on the carbon on the right, I'm going to switch where the bromine and this is a benzene ring, but where that 6-membered ring is. So now the priority groups are here and here. They are on the same side of the double bond. So this is the this is the Z diastereomer. And these are the only two configurations for this molecule. Let's go to the next one. So again, we're looking at one carbon at a time. We'll say this one is our blue carbon, this one is the pink carbon. Looking at the two groups bonded to the pink carbon, we have a carbon and a carbon. We have 3 hydrogens and 3 hydrogens. So these two groups bonded to the pink carbon are the exact same. So we can't assign priority to one over the other. So this is a case where the alkene does not have E or Z stereochemistry. Because one carbon is bonded to the same two groups. So we cannot assign priority of one over the other. And that carbon we're referring to is that pink carbon that is bonded to 2 methyl groups. So one doesn't have priority of the other. So this molecule does not have an E or Z prefix in its name. Next example. Let's do our highlighting. Carbon on the left, pink. Carbon on the right, blue. Looking at the two groups for the carbon on the left, the pink carbon, we are comparing a bromine and a hydrogen. Hydrogen is the lowest atomic number on the periodic table. Any other atom has a higher atomic number than hydrogen. So bromine is our first priority group. On the blue carbon, we have 2 carbons, so carbon bonded. Then we have a CH3 and a CH2CH3. So we have to look at the rest of this chain to find the first point of difference. The first point of difference is not the atom directly bonded to the blue carbon. So I'm going to draw out the Lewis structure of each of these. So our CH3 group, and then CH2, CH3. And then we'll use this yellow highlight color as we're comparing. So looking at what's directly bonded to the blue carbon, here we've got another carbon and then another carbon. So we need to continue looking down what's bonded to the blue carbon, those two different groups, to find the first point of difference. Carbon, I need to use different colors. So we'll make this one orange, actually. So orange carbon is bonded to a hydrogen. Yellow carbon, also bonded to a hydrogen. Orange carbon, bonded to another hydrogen. Yellow carbon, also bonded to another hydrogen. Orange carbon, bonded to a hydrogen. Yellow carbon, bonded to a carbon. So there's our first point of difference, this hydrogen and this carbon. So now we compare the atomic number of hydrogen with a star and carbon with a star. Carbon has a higher atomic number, so this is the first priority group. The priority groups are on opposite sides of the double bond, so this again has E stereochemistry. To draw the diastereomer, we can switch the locations of substituents on either the pink carbon or the blue carbon. I'll do the pink carbon this time. So hydrogen here, bromine here, and then on the blue carbon, we keep the groups the same, CH3, CH2, CH3. Priority groups are now on the same side of the double bond, or the same side. So this is Z stereochemistry. All right, we'll end the video here. We'll do some practice in class, and I'll see you all on Tuesday.